Hi. So in this video, we're going to look at the concept of work and kinetic energy as applied to rotational motion. Okay. If you remember in translation motion, when you applied a force and created displacement, we said we did work, right? And we represented this work saying work is equal to F dot S, which is the dot product of force and displacement, right? And in case we said if the force was variable, we said the work was equal to integral F dot ds, right? When we come to rotational motion, if we apply a torque and we create a change in angular displacement, then we say work is done, right? And using the symmetry in from translation motion, we can say yes, the work will be equal to tau dot theta, right? Where tau is, we know, is r cross f, and theta is the angular displacement. I wanted to remind you over here that remember that both tau and theta are vectors. Tau is r cross f, which is the cross product of r and f, and we know the direction by right hand thumb rule. We know how to calculate the direction of tau. The direction of theta is given by the right hand rule. I have said it in an earlier video. You curl your fingers in the direction of theta and the thumb points to the direction of theta, right? So therefore, it's a dot product of two vectors. Let's say tau is varying, then we say work is equal to the integral of tau dot d theta, right? Uh, which is almost, you can say, pretty intuitive following from this. Now, when we know that, let's go back to translation motion. We know that when you do work, you change the kinetic energy of a body, right? And kinetic energy was the energy of a body by virtue of its state of motion, right? And it was given by, kinetic energy was given by half mv squared, right? Yes. So this has, and when body is in pure rotational motion about its axis of rotation, it has kinetic energy, and this kinetic energy is called rotational kinetic energy, and we represent kinetic energy, rotational kinetic energy, by half I omega square, right? Which is half into the moment of inertia into angular velocity square. So this is how we calculate rotational kinetic energy, right? Which is the energy by virtue of the state of rotational motion that a body is undergoing, right? And it's clear that from here on we should differentiate whether a body is having translational kinetic energy or rotational kinetic energy. And in some cases you will find where a body has both. And therefore it is important for us to understand these two kinetic energies, which is by virtue of its motion, one being translation and the other being rotational. Now we connected both work and kinetic energy because work was just a transfer of energy, right? And the transfer energy created a change in kinetic energy, and we saw this with the work kinetic energy theorem. And here now next we apply the work kinetic energy theorem to rotational motion. When we looked at translation motion, we know work, that is F dot ds, was clear change in kinetic energy. Okay, let me put it down. This work. So we knew that work, which was F dot ds, was equal to, in translation motion, was into the change. The net work done is equal to the change in kinetic energy, right? But this is the final, and Vf as the final velocity and Vi the initial velocity. The work that we did was translated into, I'm saying W, right? This is W, into change of kinetic energy. The same theorem applies here. The work that we do is integral in rotational motion is tau dot d theta. This translates into the creates a transfer energy, which is the change in rotational kinetic energy, which would be half I omega final square minus half I omega initial square. Okay. Hence, we see how the concepts of work and kinetic energy are applied to rotational motion.